Good afternoon, this is Schweitzer, and this is a smart video here showing our lecture notes on how do we start modeling molecules. We learned the last section that covalent compounds, they have a very unique thing where they form molecules. How do I go about modeling that, showing it? Well, first we're going to start by drawing electron dot diagrams. Okay, so for this, we should note the number of valence electrons can be determined from the periodic table. If you didn't know this, you would want to. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so this boron is located right here, so it's got one, two, three valence electrons. We've already done electron configurations and stuff, so I mean, this stuff should be very similar. 1, 2, 3, 4 is how we typically draw that. Sulfur's got 6. 1, 2, 3, 4, 5, 6. Same as oxygen. 1, 2, 3, 4, 5, 6. Hydrogen's got 1 and fluorine's got 7. 1, 2, 3, 4, 5, 6, 7. So for oxygen and hydrogen and fluorine, draw out the orbital diagrams justifying the valence electrons. Okay. So this is going to be a little bit of a review, so we'll do this quickly here. So orbital diagrams just sort of justifying how we got this, this, and this one. Okay, so oxygen, 1s2, 2s2, 2p, 2p3, 2p4. All right, so these last two right here are where we're getting these electrons. Okay, that's the 6. Completing my orbital diagram, by the way. This one's going to have to get squeaked in here a little bit. Following Hund's rule. So I have 2 open spots. There's my arrow. Okay. Draw next one higher. Hydrogen. Just 1. 1s1. There we go. Fluorine. 1s2, 2s2, 2p5. 5 plus 2 is 7. There's the 7 dots. And fluorine. Arrow up, arrow down, arrow up, arrow down. I'm going to do 3 of them, because there's 3 suborbitals, and we'll match them up nicely. Okay. H2O in the molecule below. Add electrons contributed by each hydrogen as a dot, and electrons contributed by oxygen as x's. Okay, so I'm going to put a dot here, and then x there, x here. So what I did here was I said it basically could do a little easier like this. Combine these two, and you'll start to see kind of the general outline of how we model these things. Looking to overlap like that. We're going to share here, so this is maybe the best drawing right there. Alright, not perfect, but it's good. Okay, and we're sharing. So overlapping orbitals, this guy here is from the hydrogen. This guy here is from the hydrogen. And they're sharing between the two. We all want to get a full shell. That's kind of the general idea. Alright, so sketch those diagrams only using valence electrons and show how the atoms share. So fluorine looks like this. 1, 2, 3, 4, 5, 6, 7. Missing one spot. So I get another fluorine. 1, 2, 3, 4, 5, 6, 7. I could just overlap those two. When they'll share together, we'll share those two, and sometimes they draw a little line across here showing those two are being shared. 1 electron from each. O2. 1, 2, 3, 4, 5, 6. And you go oxygen. 1, 2, 3, 4, 5, 6. So we'll share here and we'll share here. That's going to give us this. It's very important just to be able to kind of see how that goes together. Nitrogen. 1, 2, 3, 4, 5. Nitrogen. 1, 2, 3, 4, 5. These two will share here, these will share here, and these will share here, giving us a full shell. Nitrogen, Now we're looking to fulfill here what we call the octet rule. The octet rule states that we're looking for basically 8 electrons in outer ring. Or outer energy level. Alright, carbon dioxide. Carbon looks like this. Oxygen, 1, 2, 3, 4, 5, 6. Another oxygen, 1, 2, 3, 4, 5, 6. Okay. So the carbon needs to share 4. Share here, share 2 this way, and we'll share 2 this way. And there we go. Oxygen, double bond carbon, double bond oxygen. There we go. And then, now that's the, the sort of piecing it together on your own visually. But you can't always do that. So we'll have a little more of a detailed version. But so symbol, single bond, double bond, triple bond, 2 electrons, 4 electrons, 6 electrons. Remember, each of these is worth 2 electrons. Bond length, okay, so bond length gets shorter as you go down, and bond energy increases as you go down. Bond order is another way we just kind of sort of a numerical way we describe these. 1, 2, 3. Okay, bond order. Next step. All right. So this is the more of the procedural way which we do this. Okay, because you can't always just piece together. It takes too long. This is the general process you want to go by. It's accomplishing the same thing. First of all, inventory. So what we do here, we get our number of valence electrons. Hydrogen only has 1 valence electron, but there's 2 of them. Oxygen gets you 6. Gives you a total of 8 electrons. This thing almost always needs to be even. Okay, almost always. Skeleton structure. Hook everything up with single bonds. Single bonds. So, oxygen, single bond to hydrogen, single bond to hydrogen. Now this thing, the angles and stuff, this model's not good enough to show that. So it doesn't matter. Typically you just go 90 degrees even though it's not 90 degrees. Okay, now this is the total number of electrons I get. So step 3 means add electrons trying to fulfill the octet rule or the duet rule. Duet meaning 2. So once hydrogen bonds, it has everything it needs. Okay, and you cannot add anything more. So at this point, I have 2, 4, 6, 8. Do not give the hydrogens anything else. Fulfill an atom all the way full and go to the next atom. But these guys are full, and I've reached my maximum. So add electrons, stop. So give everybody 8, or occasionally 2 if it's hydrogen, and then move to the next atom. Okay, keep going until you run out, until you use all electrons. And the last step is that we'll share if we need to. If we have to, we'll share, but we may not have to. All right, we'll see some examples where we got to do more. What do I do with extra electrons? What do I do if there's not enough electrons? These are some things that we'll look at in the next couple of examples. Okay. Here we're going to form doubles and triples. Here we'll put them in the central atom. You can feel free to put that in your notes if you'd like. But we'll show examples of that coming up here in 2 seconds. Alright, so next one. So CN -1. How does this work? Okay, so first of all, inventory. So carbon's 4. Nitrogen is 5. Negative means you gained an electron. So plus 1 equals 8. Well, 5 plus 4 is 9 plus 1. That's 10. Alright. Keep in mind, even. Skeleton structure. So really, this is completely just following directions. Some people really like this because there's less thought involved. But that's just the way it goes. We got to be able to think a little bit. 2, that dash stands for 2 electrons. 2, 4, 6, 8. I filled it at 8. Move to the next guy. 10. Done. 10. Can't go any farther. That's my number, 10. How many pairs am I short here? I'm short 2 pairs. So what we do when we're short, we take off a neighbor, scratch them on nicely, and move them between. Then now those electrons count for everybody. Does nitrogen have 8? 2, 4, 6, 8? Yes. Does the carbon have 8? Yes. 2, 4, 6, 8. Done. When we have a negative charge, or any charge, we put it in brackets, and we list that charge on the upper right-hand corner. Oxygen, okay? Again, we've kind of seen already what this looks like, but 6 valence electrons, and there's 2 of them. That's 12. So 12 is what I get. Skeleton structure, 2, 4, 6, 8, 10, 12. How many pairs am I short? I'm missing one. Keep on going. Don't jump around. Just fill it in. Go to the next one. Now I know I'm missing a pair. Cross it off and share between. No brackets required. You could put brackets on if you want, but there's no charge. No, it's not wrong. Just no charge listed. Next one. All right. NO3, NO2. This is nitrate. This is nitrite. Okay. So 5, and then 3 times 6, 18 plus 1. So 18. So we got 18 plus 5. That's what, 24? So this has got 24 electrons. Alright. So nitrogen goes in this. Now, give myself a little bit of room here. We're going to see something that's a little bit different here. Alright, so the nitrogen goes in the center. Oxygen set up a skeleton structure. 2, 4, 6, 8. Again, I'll fill in the center one first, so don't forget it. 4, 6, 8. 10, 12, 14. Fill it all the way before we go to the next one. 16, 18, 20, 22, 24, 20. Oh, can't go any farther. I'm short a pair. Take off the neighbor and share between. I need a bracket and I need a charge posted. Now, when scientists investigated this guy, okay, they found that all the bond lengths were the same, and they were about 2/3 of a single bond. So they weren't quite single bonds, but they weren't quite double bonds. They were someplace in the middle. And in fact, they sort of calculated it was about 1 1/3 bond each one. The bond order actually is 1.3. So the idea here is that this double bond is actually being shared between these, because it's completely symmetrical. This could have been here, there. Now the atoms don't bounce around. That's too heavy, too much mass. Electrons, almost no mass. They bounce around relatively easily. We really don't understand what electrons are, for that matter. They can move like this. It's not something like billiard balls as are in our everyday lives. It's a different substance. So the way scientists have done this is they've just decided to be a little cruel to chemistry students and say, we're going to make you draw out each one. And that's what we do. So I draw it out, double bond on the bottom. Make sure your dots are correct. And the oxygens, of course, are here. And then, there we go. And then we have there we go. And then we have this guy. Try it on your own. This is 5. And then we have 6 times 2. 12 plus 1. 12 plus 18. 18 electrons. So, again, I'm going to give myself a little room because we're going to what's called this a resonance structure. I mentioned it before. I'll write it down in a second. 2, 4, 6, 8, 10, 12, 14, 16, 18. Short a pair. Take a pair off a neighbor and share. So now I have 2 bonds resonating. Bracket it up with the charge. Go back and forth to each version. Don't forget to add all your electrons. I'm going to get rid of one of those guys. This one's got 3 pairs, but the other one's only got 2. bracket it with a -1 charge. Again, we call these resonance structures. Resonance. Resonance means to vibrate, or that's a C here. Resonance structures. All right, next up. All right, so a couple other examples. What do we do if an atom's violating the octet rule? We know what we do if we have too few, we share. What if it's got too many? All right, so let's try this out. Like iodine is 7. This guy is 7 times 2 is 14. Plus 1 is 21, 22 electrons. Okay. Iodine, fluorine, fluorine, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Let's add the center. So we add to center atom. Only some of these atoms can actually do this. You need to be in the third row of the periodic table or lower. That central atom needs to be in the third row or lower. That gives them the ability to have d orbitals so that they can, handle it and be bigger. SF6. When we do this problem here, we're keeping simple. So we're going to do very symmetrical like this. And you'll see that this guy automatically, when I just hook it up, violates the octet rule. SF6, add up our electrons, and you're going to find that each one is just going to be full, and that's it. So check it out, do your inventory, see if you can get it to work. There's one extra electron there. Alright. There we go. That's modeling a molecule. Okay. There's my answers for those guys. Again, a couple things you might want to know about these things. We have some shapes which you may or may not be in orbitals, which you may or may not be ready for yet. But we're getting there. Last little thing I'll mention here is just as a harbinger of things to come here, electron domains. This guy's got 5 electron domains, so that's 1, 2, 3, 4, 5. So they can be bonded or non-bonded. So that iodine atom has 1, 2, 3, 4, 5 things coming off it, and that controls its shape. All right, which is that guy right now. These two are bonded with onto fluorines, but these two guys are just having electrons in them. Okay, this guy's got 6 domains. That's one of them. There's 6 of them total. We'll stop there. We'll be picking up our next little video on properties between molecules. Thank you very much.